All right, so let's discuss what might be a better approach to solve this distributional shift problem. So we discussed before how the problem with behavior cloning is due to the fact that when you take actions, you might make mistakes which lead you to unfamiliar observations, observations that are different from any of the observations you saw during training, and then you might make a bigger mistake. And these mistakes will compound. Okay? So fundamentally, the problem comes down to the fact that p data of OT, the distribution over observations from which your training set is generated, is different from p pi theta of OT, which is the distribution over observations that you will see when you actually run your policy. So can we somehow make p data of OT be equal to p pi theta of OT? Well, we discussed before that if your policy is perfect, then they will be equal. But in general, that's very, very hard. So can we have an algorithm that is guaranteed to do this somehow, even if your policy is imperfect? Now, on the surface, that might seem impossible. Like if your policy always has mistakes, how could you possibly end up with an observation distribution that matches the true observation distribution? The key idea is that if you can't fix the policy, fix the data. So we're going to make p data of OT be equal to p pi theta of OT, not so much by improving pi, but by improving p data. So we're going to be clever about how we collect our data. Now, you can't always do this. You don't always get a choice in how you collect your data. Maybe your boss just came and said, you know, I've got this data of driving, that's what you're going to use, and you can't get any more data. You just have to use this driving data that I've got. Okay, then you're out of luck. But sometimes you do have a little bit of influence in how you collect your data. And it turns out that if you're clever about it, you can actually solve this problem. So this is a method called DAgger, which stands for dataset aggregation. The DAgger is essentially an iterative algorithm for imitation learning that collects data in a very particular way that avoids this distributional shift issue. And in some cases, DAgger can work very, very well, but in other cases, you can't use it because you can't collect more data in quite this manner. So here's the idea. The goal in DAgger is to collect training data from p pi theta OT instead of p data of OT. But the problem is that you still want supervised data. You still want data of human actions. For every observation, you need the human's ground truth action. So the way that you're going to get observations from p pi theta OT is just by running your policy, pi theta AT given OT. But getting labels for it turns out to be a little tricky. So here is the procedure for DAgger. Step 1. Take a data set given to you by a human, which consists of the human's observations and actions, and use it to train your initial policy. Now, this policy will be susceptible to distributional shift because that training set came from p data of OT. So then we're going to run our policy. Like we'll literally control the car using the learned policy, and that will produce some observations. Observations that we'll call them d pi. And some of these observations might be quite bad. It's like that first video that I showed where the car runs into the traffic cones. Like we'll actually do that and we'll record what it sees. Now obviously you need, like in reality, you need like a safety driver who'll push the big red button if something really, really bad happens. But if you're careful, you've got the safety driver, you can do this. And then what we're going to do is we're going to ask a human to sit down and label every one of those observations. Like we'll actually let the car drive, it'll hit those cones, and then we'll have a person sitting in front of like a little toy steering wheel seeing images on a screen, and we'll ask them to basically provide the steering commands that they would have taken in those situations. And we'll treat those as ground truth actions. And then what we do in step 4 is we aggregate. We have this labeled d pi and we concatenate it to d, and that gets us a new data set that now is closer to the observation distribution for our new policy. And then we repeat this process, we keep going. And we might keep going many times. Now, you might say at this point that, well, wait a minute, it doesn't seem like this should work, right? Because you said that you want p data to match p pi theta, but you're just combining them, right? Well, the intuition for why this actually ends up working is that if you combine them enough, eventually the data set will be dominated by data from p pi theta. So eventually those distributions will get arbitrarily close. In practice, you don't even need to wait that long. In practice, you actually get good performance long before that. And there's actually a more nuanced theoretical explanation for why that's true. But If you want sort of the short, quick, and dirty intuition, it's because if you collect enough data, eventually the p pi theta samples dominate over the original samples. So this will fix distributional shift. This will actually, honest to goodness, fix the problem. And if you can do this, it works very well. And this is a video from the original DAgger paper that shows the DAgger algorithm trained to fly a drone around some trees. Now, this is actually, this is somewhat older work. It's from 2011. So they actually don't use deep learning, although more recent versions of the system do use deep learning. Here they actually just used essentially something like a logistic regression style model. Okay, so that's the DAgger algorithm. Now, what's the problem with DAgger? So far, I've just told you the good things, that it fixes the distributional shift problem. The issue with DAgger usually is this third step, and sometimes the second step. So the second step can be a problem if it's really unsafe to run your system, or if it's actually impossible. The third step can be a problem because humans are sometimes not very good at making decisions when the system doesn't react to them. So it's a very unnatural way to collect data, where you're like driving the car, but the car is not actually responding to you. And therefore, humans sometimes can't give very good labels, right? So this can sometimes be very difficult. Now, there are a variety of ways to mitigate this. Like you could, for example, have situations where the human actually takes over and actually provides corrective driving commands, and that can also work too in some cases. But in general, the main flaw with these kind of DAgger-style algorithms is that their data collection protocols are a bit more onerous. So it's very appealing to just take a data set, run behavioral cloning on it, and immediately get a policy. It's not quite as appealing to have to redeploy that policy in the real world, collect more data, get more human supervision, and so on. Okay, so summary and takeaways from this discussion. In principle, behavior cloning should not work because of the distribution mismatch problem. In principle, DAgger can address this, but it requires costly data collection and labeling. But it is a principled solution to the problem. That said, sometimes behavioral cloning works well anyway. It requires a little bit of heuristic hacks and very good high accuracy models. So my recommendation, if you want to solve an imitation learning problem, is to try behavioral cloning first, but prepare to be disappointed. So try behavioral cloning, do your best, but if it doesn't work, that might just be how it is. And then you need something smarter, like DAgger, or the reinforcement learning methods that we will cover next week. So next time, what we're going to do is we're actually going to discuss the second and third bullet points. So in today's discussion, we mainly talked about the problem of non-IID data, but we still assumed ground truth supervision. We still assumed that the human actually gave us the ground truth actions that you're supposed to take for a given observation. Next week, we'll talk about the full reinforcement learning setting, where instead of the ground truth action supervision, you're given some high-level goal in the form of a reward function. And we'll discuss algorithms that can learn policies to successfully accomplish such goals. So we'll tackle these with reinforcement learning next week.